will pass I will pass over to our colleagues. Welcome.
Thanks, Lee. Thanks for the invite for the three of us to come and talk to you about this. It's a nice intersection of data science and thinking about health equity. Turns out there's a group that does that, so it's really interesting to present what we've done in that context here. So we can introduce ourselves as well, but just to start with, I'm Frank Wood, Chief Analytical Officer in the Leeds Office of Data Analytics. That's a joint analytical service for Leeds City Council and the commissioning bit of the NHS, West Yorkshire ICB in Leeds. I'll pass to Anna to introduce herself and then Rob.
Thank you, Frank. So I'm Anna Palczewska. I'm Senior Data Scientist on the Network Data Lab, and I'm a former academic leading a small analyst team on the Health Foundation Network Data Lab project.
Yeah, my name's Rob. I'm a data scientist from Accenture, specialising in healthcare analytics, and did quite a bit of work last year with Frank and Anna on some really interesting stuff we're going to talk to you about today.
So we've got some slides to share. There's a level of technical expertise on this call in two out of three of us. So if you want to get into more detail, please do. Or if it's too much, just say we can kind of recap stuff. So what we plan to do is run through the slides and then have a bit of a chat. If you want to interrupt or ask questions as we go, you can. We'll try and still keep to the time that we've agreed. But yeah, that's fine too. But just to give us a bit of a starting point, I'll see if I can share stuff. Can you all see something?
Yeah.
Yes, perfect. So that's working. I don't. Yeah, okay. So you know we are, we're here. And as I say, that focus on partnership work. So just to set some of that context, I'll talk about the background of something called the Leeds Data Model, which we developed through some data science. I'll come back to this slide in the wrong order. So the Leeds Data Model is a commonly pseudonymized linked series of data sets for health and care for people who are on a GP register in Leeds, and people who on that register have agreed to not opt out, so we can use their data for planning, evaluation. We can do quite a convoluted process, re-identify people through that data, but its purpose is for planning and evaluation, looking at population health need. On the strength of having this model, it meant we could work with Accenture because they had already built, Rob and colleagues had already built a predictive model to forecast health outcomes using an American healthcare data set. And we had a version of that using NHS data and local data sets that include, as you can see on the screen, housing data is in it now. It wasn't then, but adult social care and palliative care services and other data they want to bring in. So anything that's in, if you part of the NHS health informatics world, anything that is a national commissioning data set, it includes that. And it also includes primary care data that we've got local agreement with GPs to extract, adult social care data because we work in partnership with Leeds City Council, as I said, and bringing in housing data. So it's got quite a broad range of data, and it gives you that longitudinal data set in terms of a person's interaction with healthcare in Leeds and where they've used services more widely. I'll just skip back a slide to that running order of what we did partnership-wise. So, as I say, we have actually before 2015, but we've had that Leeds Data Model. We worked with the initial national pilot with NHS England to develop what population health management should be, again using that data model. On the strength of that model, the Health Foundation very kindly gave us some money to be part of their Network Data Lab, which is just about at the end of its programme, with a massive big finish with Anna joining us as the senior data scientist funded through the Health Foundation. Again, that's the connection to this meeting and yourselves. We then began to work with external kind of non-NHS, non-public sector partners in 2022. So we first of all worked with UST Global, we kind of developed a version of a data science environment using Microsoft Azure with UST. A bit clunky, but it did work, and we got a bit of modelling out of that partnership. Because we've done that once, we could do that again. So we got to work with Accenture, as I say, to develop this model. Improve the environment, improve the access and control of access to that environment to make it a bit slicker, and that's where we got to be able to develop the data that we're describing in the later slides and the outputs that we got. Following on from that, some kind of work last year and into this year that's just begun, so we can use the same approach to model different health outcomes. Use a transformer model to see if we've got a different level of precision or improvement on the results. So we're continuing to evolve that, and then I don't think it's on this slide, but if there are partners out there who want to do this work with us, the tagline will be, if you've got the knowledge, we've got data. So get in touch. Okay, I'll move over to back on track. So in this context, we're thinking about the equity of implementing disease prediction models. And there's the equity of the model, which we'll expand on further through Rob and Anna's presentation. But that model is in the context of how people really access services in the first place. Is their data captured? Are they known to service? And then subsequently, how you then implement the use of the results of that model in an equitable way, and what you need to do to mitigate the risks of reducing equity as a result of having a model that only applies to a certain section of the population. Well, I can expand on that when we get to the end of that. I think see to Rob.
Cool. So should we jump to the next slide? And I can talk you through a little bit about kind of what we did, and then Anna's going to talk through some of the stuff we did around fairness, explainability, and that kind of thing. So this came about initially as an idea which we had for a different way to look at risk prediction using deep learning. Obviously, the promise of AI in healthcare is huge, as many of you may have seen, and there's loads of really exciting stuff happening in research papers, but very little of it seems to filter through to actually improving outcomes for patients somewhere. So what we wanted to do was see if we can figure out how to take some of the exciting stuff out of research papers and then genuinely deploy it in the real world and use it. So we came up with an approach which we tested on an internal Accenture database, which we have from in the US, and then we brought that to Frank and Anna and said, can we come and try this with you? And that led to a very fruitful collaboration, and that's why we're here. I'll talk, if we jump to the next slide, I can talk a little bit about the methodology and why it's different from a kind of typical approach to predicting disease risk. So typically, if you wanted to build a model to predict, for example, who's at risk of developing diabetes or hypertension, you'd start with an expert clinician who would tell you what features you needed to go and look for, and then you go away and you'd kind of find those features in the data and you calculate them and you kind of build your model up like that. What we wanted to try was more of a kind of data first machine learning approach, where we allowed the model to figure it out from large, massive amounts of data. And what we came up with is a little bit like a language model, or a natural language processing type algorithm. But what one of those models will do is basically it will model a sequence of words in order through a paragraph. And then it will make predictions about what comes next. What we did is we modeled sequences of medical codes, so SNOMED codes, ICD-10 codes, OPCS codes, etc., which make up someone's patient history over time. So basically, the model can read, quote unquote, your whole medical history from end to end, and then make really detailed predictions about what's likely to happen to you based on your kind of overall trajectory over time. So if we're predicting diabetes, say, which was one of our use cases, the model would look at patient A's history and it would see that there are codes there for obesity, high blood pressure, high BMI, and hypertension. So it would kind of pick out those features and be able to say this person is highly likely to develop diabetes, whereas patient C, who's got a bit of bronchitis and a cold and a broken arm, I mean, I'm not a medical doctor, but even I can see that they're not risk factors for diabetes. And then, as Anna is going to talk more about, we made this explainable so that you could actually go to a clinician and say, okay, this person is, the model has said this person is at risk of diabetes for these specific reasons. It's a really simple approach in essence, and it works really well for lots of papers in the research literature. What we found is that when we deployed it, it worked really well for us as well. And the nice thing about this approach is that it scales really easily across different conditions. So you don't need to find an expert clinician for every condition to tell you what to look for. You can kind of use the same approach multiple times and then use the clinician, as Anna's going to talk about, to validate. So they're still in the loop. It's still really important that they're involved, but hopefully less arduous on their time. Can we jump to the next slide? So in the end, we developed models for about 15 different long-term conditions, but we did quite a lot of benchmarking with diabetes because there's quite a lot out there already for diabetes. And we asked ourselves two key questions. One was, is this deep learning model any better than what is in use today? Because there's no point having a much more complicated way to answer a question that we can already answer. And then secondly, does this model tell us anything new? Because doctors do know what causes diabetes, and I suspect a GP could point to you which of their patients are at risk. So we wanted to say, does this actually add new information into someone's workflow somewhere, theoretically? So the first question, was it more accurate than what exists today? We did a bit of a comparison to other models that are in use in the primary care record. So there's one called the Diabetes UK model, which you can actually go on, if you search for it online, you can go and input your details into that and it will give you a risk score for diabetes. With that one, we found that out of every 100 patients who are identified as in the highest risk category, 14 were true positives. So 14 would have diabetes within 3 years, but the others were false positives. They might have been at risk, but they didn't develop diabetes in the next 3 years. And similarly for Q diabetes, which is a slightly more complicated statistical model that's in widespread use, that was 19 out of the 100 patients who went on to develop diabetes. Whereas with the deep learning model, 56% of the top risk category would go on to develop diabetes within 3 years. And as you can imagine, that has real implications for the cost benefit analysis of then trying to do a preventative intervention with those 100 people. Because if you've got to do an intervention with 100 people just to find or stop 14 potential cases, that's nowhere near as cost effective as being able to maybe prevent 15. So yeah, I definitely found that it was more precise than what's in use today. And then the second question, does it tell us anything new? We did a bit of a retrospective analysis and we ran the model on the 1st of January 2018, and then we followed the patients that were predicted as high risk over the next 6 years to see what actually happened to them. And we found that out of the patients that the model identified, about half of them got referred to the NHS diabetes prevention programme, and there's a record of that in their GP record, which is great. But that means that just over half of them didn't get referred, even though if we'd had a deep learning model 6 years ago, we could have known that they were at high risk. So we do think that adding this type of modeling into patient level workflows has lots of potential, obviously, with all the caveats around early days, lots more testing, lots more governance needed, etc. But we're quite excited by the outcomes of this proof of concept in terms of the potential it has. But obviously, before you can do any of that, there are lots of additional safeguards that you'd need to do. And I think I'm handing over to Anna now to talk about some of the work that was done around explainability and fairness.
Thank you. Thank you, Rob. So, as Rob mentioned at the beginning, when we are thinking about the approach, which is more data-driven, and we are applying more advanced technology, and we are coming to the point that AI model become, around our pockets, and we basically can start using them. To make them used in healthcare, we cannot leave them on their own. We have to have a way of controlling them and make sure that they are transparent and actually they make reasonable decisions. So the explainability and the fairness comes to that point which allows us to assess those models and identify the artifacts about the model which hopefully help clinician and commissioner to understand how they work and then gain a trust in applicability of those models. Can you move to the next slide, Frank, please? So this slide shows you how we thought about the responsible AI process. So rather than building a model first and then asking whether it's safe or fair, responsibility is designed from the very beginning. So we started with electronic health records and we used them to train the models which we wanted to use for the decision support decisions. As the model moved through the training, we built the several layers of assurance. We look at the factors that the model is learning, whether these factors align with clinical understanding and wherever the outputs are explainable and interpretable. Techniques like explainability and expert validation allowed us to check that the model behavior makes sense, not only statistically, but also clinically. A key part of that process is that human oversight. Clinical experts review our outputs, challenge assumption, and validate whatever results are plausible and useful in practice. So in the journey, we have used the expert knowledge in terms of identifying a potential target cohort, help us to identify the inclusion-exclusion criteria, analyze the artifacts of the models, and eventually assess the fairness. So the fairness was tested and carried along the sides when we were developing the models, and we tried to identify whether the prediction behaved differently across the groups and understand why it happened. So once the human is involved in that loop of the process development, is also designed for the human who sits at the end and would like to use that model for on the population level to understand the development of the certain long-term condition on the population level, as well as a clinician who would like to look for the individual patient risk and understand why the model scored that patient highly. So Frank, can you move to next slide, please? So this is how we go about. When we look for the key points related to responsible AI, we look for the transparency. So we want to understand the data and the provenance of the data. We look for the explainability to understand the artifacts about the models and why the model makes that reasoning. We look for fairness and bias to make sure that certain groups are not disadvantaged by making unfair prediction, and then that helps us to bring accountability of that models, having that human expert involved in the process, and eventually we are hoping to get a trust in being able to apply this model in the real cases. So to understand the model, we've been using the SHAP values, which stands for the Shapley Additive Explanation. And here's the example of it. So the top row is showing you the overall contribution of the certain feature towards the potential predicted outcome, and the bottom row is showing you a data point. So you have the individual patient and the magnitude of the contribution towards the likelihood of developing a condition. The red side shows you the positive increase of the chances of the particular condition. The blue dot showing the negative, just reducing the risk. So you might notice once you analyze the feature contribution that the certain features might be showing you that condition or early signals to develop the condition, whereas certain features might provide the preventative information. So, for example, the patient having a certain type of the feature actually which might reduce your likelihood, can be treated as a preventative. So what are the sharp values? So this methodology was developed around 10 years ago, and it basically helps to break the model prediction into understandable parts. And that comes from the game theory, where each feature is basically treated as a player, contributing fairly to the final outcomes. So from those features, we can ask the question like, which factor matter most? Did the factor increase or decrease predicted risk, or are these influences clinically plausible? As I mentioned before, it can be done on the individual level, explaining the pattern of the model or the model behavior in terms of reasoning. You might notice that might be several patterns across the population. As well, you could look for individual level and understanding the signals for the single patient. So what is important to mention here? This explain the model reasoning is not causality. And when you apply to the longitudinal models, we can see which feature contributes more strongly to the prediction, and also at what point in time this feature began to influence risk. So this allows us to distinguish between early signals that appear well before the developed condition, or late signals that reflect established disease. So Frank, can you move to the next slide? So when we look at our diabetes example, what you could see are on the left side are the top of our 15 features. And what you could see is roughly the scale of the importance of how this feature contributes towards the diabetes. So because we are working with SNOMEDs and the procedural codes, we have a large number of those features. So we are talking about 20-30,000. And sometimes, as you could see, some of the different features might be repeated, but what it might be changing is the units or the beans related to the particular testing or the lab test. So what we wanted to understand is how we can translate now those codes to something which will be understood by clinicians or even patients. So we can start analyzing this feature contribution, and we can understand the specific themes, and we can group the certain features which can reflect the certain scenarios, and just link them to the model prediction. So in this example, what you could see is, for example, strong drivers related to the hemoglobin level, HbA1c, glucose level, BMI, which are related with the condition. But also what you could see some socio-demographic factors related to the ethnicity or the style of the life, which also impact diabetes. So this feature can allow clinicians a sanity check on the models, explaining why the model makes predictions. So once we present the model to the clinician, they can say, okay, I understand why the model makes the risk. And that basically is in line with the well-known population health evidence, but also allows to look at individual level. What do you expect when you're analyzing the feature contribution? That basically most of these features or the themes will align what is already known with in the literature, but also you might find some specific outliers for specific patient, finding something surprising, and this is not necessarily will be the model error, but that might open a new area where the certain conditions were not considered yet to analyzing a particular disease, and open a field for extended research. This also allows to understand the model behavior, because when you start grouping the certain pattern across the larger population, you might notice that actually the certain feature contribution might fluctuate between the different groups, and you might basically isolate the different pathways of decision for the model for specific subgroups of the population. So can you move to the next slide, Frank? So once we gather these artifacts related how well model perform and what are the important features, we discuss them with clinicians, we kind of confront them with the literature. So we make sure that the model basically stands and provides that evidence related with the general population health. We also would like to estimate if the model does not disadvantage any groups. To do it, we are looking for the following metrics. We decide what are the most sensitive or most important feature we would like to analyze against. In the healthcare, we're quite often looking for personal characteristics like gender, ethnicity, age, deprivation, or the certain location. And we are looking for demographic parity, so we are asking if the prediction rates are similar across this group. We are looking for equalized odds, where the errors are similar across the groups, equal opportunity if the true positives are comparable. We are looking at the calibration because we would like that the model match the actual outcomes within the groups. And also there is a potential to run like counterfactual testing, asking if we change one of those kind of sensitive information or attributes about the patient, does the model shift unfairly in one or other direction. So combination of this test gives us a confidence that the model is not just accurate overall, but also behaving appropriately across the various population group. So if we go to the next slide, we have an example for the ethnicity and our diabetes model, when we've been looking for the distribution of the likelihood for each group having and not having condition for the data set we used to develop the model. And also we were looking for general the area and the curve as a model perform overall also for each separate group. And what you could notice there, you can see certain variation on the area and the curve, but this is not a massive shift that one of the group is performing very poorly. They all have a significant performance. And when you look for this individual group in terms of the model risk, you might notice that you have a quite nice separation between this positive and negative groups. There is some variation here for the unknown and I think mixed ethnicity background, but this is what we notice in our data. Quite often these two categories are not very well recorded. So we don't have, obviously unknown is quite an important element in the data to not having a coded ethnicity, but that doesn't mean that there's a problem with the model. It basically flagging to go back and revise your data set and understanding that variation on in your data set. So that was the example only for the one characteristics, but you can take it further to start comparing with other models, and I will pass it to Rob.
Oh, thanks, Anna. So, if we go back one, yeah. So as well as doing the fairness assessment across different groups, as Anna's just been showing, we also wanted to, again, compare it to what exists today and see whether the deep learning model was showing more difference in performance across different ethnic or deprived backgrounds, etc., than the Diabetes UK model. So what we actually did is we calculated the performance of the model. This chart, it shows you by ethnicity. And what we found was quite interesting. We actually found that the Diabetes UK model, even though it's very simple and rules-based, in this particular population where it had been applied, it was performing quite differently in different ethnic groups. That might well be because it weights ethnicity very highly in the way it generates the outputs. So you'll see if you go and have a look at it that you get kind of points based on how at risk your ethnic group is. Whereas the like a more advanced model is able to balance those factors against all of the other things that are going on in your medical history. But yeah, the headline was that we found that actually overall a deep learning approach could give a less biased a less biased model than some of the simpler models that exist today. And just because a model's simple doesn't mean it can't have some inherent bias in it, certainly in a particular population. We didn't do a comprehensive assessment across the whole of the UK or anything, so we are looking at one specific population where these two models have been applied. But yeah, in this case, well, this is what we found. We jump to the next one. And then the other thing we did was this left behind analysis. So obviously for patients with very little information in their medical history, it's difficult to train any kind of model to predict their outcomes. So we had a threshold of 20 items of medical history, and we discarded patients who had less than that. So that meant that we lost about 4.9% of the population when we before we started training our model. And obviously we then couldn't make predictions on patients with less than 20 items. We looked at that across deprivation, across age and sex and ethnicity. And what we found was that the excluded population in Leeds overrepresented young people, so people aged 18 to 35, male people, and then people with Chinese or Indian, British Indian as their census recorded ethnicity in the GP record, and an unknown IMD score. We think in Leeds we might be capturing some of the student population here who might be less likely to have a full medical history in their Leeds GP record. And we hopefully most of those younger people are not at risk or at as much risk of some of the long-term conditions that we're trying to predict. But definitely this was an important piece of analysis to do, to understand what the limitations are and to be able to feed back into decision making, so that as it gets implemented and used, it's used in an awareness of what we might be missing, and other provisions can be put in place for those sections of the population, which I think Frank is potentially going to talk a bit more about now as he talks about user models.
So if you just look at some case studies how we could implement this model, and these are there's some frustration limitations in terms of how we could make use of the model given the constraints we have in terms of reuse of data. But I'll describe how it was used, because it's really been really quite helpful in a lot of things we're looking to do in Leeds. So thinking about that implementation at a strategic, operational, and person clinician level. So strategic level, it informed our choice of goals for what was the Healthy Leeds plan. This is being rewritten. I think that link might still work. If we share these slides, you could check it out. So there were two parts to this plan. Goal one was reducing unplanned service use in the health sector, and then goal two was preventing people becoming unwell in the first place. And the kind of area of upstream prevention within the gift of a healthcare commissioner is to look at finding cases of disease before they otherwise occur in a population where they're likely to occur. So this model was perfect to support doing that, looking at hypertension and COPD. And then that prediction of COPD was used to set a primary care incentive scheme in terms of the numbers of expected people in a population you could find in the next 12 months, and that helped set targets for general practice, the incentive scheme, the GPOP incentive scheme. At a personal clinician level, so as I said, it's not straightforward to re-identify people from the data that we hold, and some people aren't in those data that we've used, but it does give you a kind of a case definition of the characteristics of who to look for people with undiagnosed high blood pressure, or certainly people who you would predict from this model would have a GP recording of hypertension within the next 3 years. To support our discrimination of those population groups and where to look within Leeds, the model was model outputs were reproduced in a Power BI dashboard, which helped kind of generalist informatics teams make use of the predictions that we've seen so robustly put together by Rob Banana and other colleagues from Accenture. And again, that summary of where to look it's kind of simplified here into breaking down the population who we've got data for in terms of predictions by demographic characteristics, so gender, the area deprivation within which they live in terms of season multiple deprivation, decile 1 to 10, their broad ethnic group and age band. So we could look at, because we've got person level predictions, we could aggregate these data into any of those characteristics of interest and use that prediction of future new cases in that particular subset of our cohort to work out where the greatest change in number of people would be by each of those different cohort characteristics. And that's what that table summarises there. So there's a greater proportional increase in diagnosis in people living in areas of greatest deprivation, a greatest proportional increase for people, particularly from mixed Black and Chinese or other backgrounds. And the age range of increase was lower than perhaps expected prior to looking at these data. So that informed, again, that targeting of that goal to prevention work in Leeds as part of an early detection CBD program. Okay, so this is the newest information, and you can jump in on this any time you want, because I may undersell what you've put together here and what the model does. So because we could run the model against a patient record level data set, excuse me, we could test those predictions against that data set after a period of time had passed. So about 12 months since the model was originally run, we could then look again at people who are still within our data set and see whether they actually did develop the condition or not. And this hypertension example is that. I should pass it on because it says that on the slide. So stop talking about it. Don't speak any about that.
Thank you, Frank. So yeah, we wanted to look at how many patients actually develop the condition within a year, even though the model predicts 3 years. So after 1 year, our baseline was on around 5% for entire models. But when we try to stratify it based on the risk the model produce, then we wanted to observe where we have a higher lift within that group comparing to kind of baseline for entire model. So we, because the model was calibrated to the population risk level, so we've been looking for the risk group above the 20%, then 10 to 20, 5 to 10%, and less than 5%. And what you can notice is that the final column is the lift, is literally how much time, what was the observed rate higher above the baseline rate. And then you could see that in this group with a higher risk, actually the lift is around 4 times, which basically shows that the model strongly stratifies that feature hypertension risk in predicted population, and the patient with those higher risk are literally 4 times more likely to develop hypertension. So that the highest group could be a potential group for targeting if we could re-identify the people and go to kind of practice level. But from the commissioning perspective, we basically could understand what might happen in the population overall. We also have run some comparison how that works against the certain features and try to identify where the models have a higher risk against the ethnicity, age, and we could then identify based on that validation that the model stratified the different groups very well, so we don't see any unfair shifts in terms of the higher number of the prediction for the particular group after 1 year validation, and then help us to target the specific group of the population for potential intervention. I pass back to you, Frank.
Excellent. Yeah, so just bringing that back to that skeleton diagram I showed at the beginning there. So we've hopefully from this presentation you can see that the test, understanding and validation of the equity of the model itself was really thoroughly done. And that's that midsection I've summarised. All that could work into just a few bullet points there. But we've got to think about how this is implemented in that real world. So as I'd alluded to at the outset, there's a risk of not finding people because they never access the service in the first place, so their data isn't reported. So we need to be cognizant of that in terms of population groups that wouldn't be in the model as a result of that. And then at the other side of the new idea, the model, the equity of the model testing that we've done, that real world implementation, there's then that equity of that implementation. So who was excluded from underlying data set? Who does the model exclude for good reason? And the applicability of the model and the utility of the model, you need to exclude people with low numbers of healthcare events because it can't predict if there aren't any events to use. And then there's an exclusion through how that model is implemented. So the example we could use in the case of the Leeds Data Model is it's a massive and valuable comprehensive data set, except for the 4% of people on a Leeds GP register who opted out of using their data for this purpose. So there's an intrinsic exclusion there, and that's people who were on a GP register at all. So if you're going to implement this kind of modelling, and you should, because the predictive power of it's higher than existing models and can be improved on further with if you use something like a BERT transform model, as I mentioned, we started to develop in Leeds. You need to make sure you're doing something with other people who were never in the model in the first place. And that's the critical point, to not inadvertently increase health and equity through the application of these really valuable tools. These make use of the kind of efficiencies of case finding that these tools allow, and then redeploy that resource through that efficiency into finding people you wouldn't otherwise be known to service. I think that might. Oh, there's a development path that. So we can move on to. Yeah. So again, that summary of the work we've done here, which is hopefully AI generated, which is quite meta really. So you kind of design the model, select a patient, look at that risk prediction, find those high risk patients, check who might be missing, and then you're doing that through that human in the loop, human oversight, clinician in the loop, as Anna described in terms of clinician review, and then bringing in their insight in terms of finding people for real. It's a decision support tool. It's still within the clinician's judgment who to target, how to treat them, and the liability would stick with the clinician. You also have the clinician's own insight in terms of who they know are missing from people they either see rarely or kind of are aware of through other family networks and people that do present in their practice. There's the fact that you could use this to target intervention very highly specifically to particular patients based on their own characteristics and entirely only on their own characteristics. And then what you do in terms of follow-up and outreach. And there's the road loops back around because you've got that feedback loop in terms of how that works for clinicians and patients and other improvements or things you may have missed in terms of what could be added to the model in terms of what you might further data sets, for instance, you might want to use to enhance that as a result of clinical findings on examination of people that weren't in the model in the first place, but they had a sense that they should be. I'll stop there, Cam. So thank you. I didn't have a chance to keep up with any